In this fourth video, we're going to look at a case of integrating a rational expression where the denominator, when factored, will have repeating linear factors. This denominator, x cubed plus 2x squared plus x, you can tell it has an x in common with all three terms. After you factor out an x, it's going to leave us an x squared plus 2x plus 1. So let's go to the next slide, and we'll look at decomposing that. So I'm going to take this fraction and start factoring the denominator. Let's factor out the x that's in common with all three terms in the denominator. Okay. Now in the parentheses, x squared plus 2x plus 1 will break down as x plus 1 times another x plus 1. Well, that x plus 1 factor is repeating. So we can write that as x times x plus 1 quantity squared. Now the catch is, when you are decomposing with a repeated linear factor, the unique factor on the bottom is just x. But when you have repeated factors, you build them up one power at a time until you reach the exponent, or how many times it repeats. For this one, it's x plus 1 squared, so it repeats only twice. But you build a fraction for once, and then you build another fraction for twice. That way. Now, as we've done in the previous videos, we're still going to multiply all the way through by a least common denominator. And so on the next slide, we'll do that. Okay, so I've just recopied from the last slide. If you multiply all the way through by the least common denominator, then, and I'm going to mark this one with a red asterisk like I had in the previous video. We're going to have the numerator from the original fraction, because multiplying through by the least common denominator will cancel that entire denominator out. Okay, this first fraction, a over x, it has the single factor x, but it's missing the two x plus 1s. So when you multiply through by the LCD, the x will cancel, but you'll still have a couple of x plus 1s remaining. The fraction in the middle is missing an x and another x plus 1. And then finally, the third fraction has both x plus 1s, but it's missing that unique factor of x. Okay. Now, as far as what we're going to replace x with in order to solve for a, b, and c, we have a good candidate of 0 and -1. Those are values of x that make those split up fractions denominators equal to 0. Let's take it one at a time. And first we're going to let x be 0. In the equation marked with the red asterisk, replace every x with 0, and you will get 6 on the left side, a times 0 plus 1 quantity squared, b times 0 times 0 plus 1, that goes to 0. C times 0 is also 0. So immediately, by substituting in 0, we get a equals 6. Excuse me, a equals 6. Now let's go with -1. Go back through the red asterisk equation. Replace all your x's with -1. I'm going to write them out this time. That way you can see exactly how it transpires. All right, a is 6, so I can replace that. On the left side, we're going to get a total of, let's see, that's going to be 5 minus 20 plus 6. If my math's right, I think that comes out to -9. On the right side of the equation, -1 plus 1 is 0, so this term goes away. Same thing in the second term, -1 plus 1, that goes away, leaving us with -c. So that tells us c is equal to 9. And finally, we just make up a number, and let's see, I'm going to just choose +1 to substitute through. Substitute 1 throughout the equation, again marked with the red asterisk. That's the one we keep going back to. 5 times 1 squared is 5, plus 20 times 1, all that is, let's see, 5 plus 20 plus 6, 31. On the right side of the equation, a times 1 plus 1 squared, and remember a is 6, plus b times 1 times 1 plus 1. C is 9, so that's plus 9 times 1. Okay, so I've run out of real estate. I'm going to move to the next slide and finish solving this equation. 31 equals 6 times 1 plus 1 squared is 24. Be careful to square before you multiply. Plus 2b plus 9. So that gives us 31 equals 2b plus 33. Solving for b, b is equal to -1. Now from the second slide where we started breaking down the original rational expression and substituting in our a, b, and c values, remember a was 6 and c was 9, just as a reminder. Whoops, there we go. Okay, so our original fraction, we had 5x squared plus 20x plus 6. All over x cubed plus 2x squared plus x dx. And that can be rewritten due to our decomposition. 6 over x minus 1 over x plus 1 plus 9 over x plus 1 squared. Okay. That big fraction, once it's decomposed, comes out to those three smaller fractions. On the next slide, I'm going to separate these into three separate integrals, and we'll tackle them one at a time. From the first fraction, I'm going to factor out a 6. From the second one, it only had a 1 for a numerator, so I'm going to actually leave it as it was. And then our third fraction, I'm going to factor out a 9. First integral, the denominator is x, its derivative is 1. That's a perfect candidate for natural log. Since x can be negative depending on what value, absolute value. The middle integral, x plus 1, has a derivative of 1. So that's natural log of x plus 1. And because that can be negative, absolute value as well. The third integral is not quite as straightforward. If we replace x plus 1 with u, then that last integral and don't forget, we're going to have to account for that dx term too. So du is dx. That's the same as 9 times the integral of u to the negative 2 du. Using the antiderivative, add 1 to the power, that's negative 1, divide by the result. That gives us negative 9 u to the negative 1 plus c, which is negative 9 over u to the first plus c. And then finally, when we change u back into x plus 1, we can finish that last integral. Negative 9 over x plus 1. There's our replacement. That gets the x plus 1. And then we finish it off with the constant of integration plus c. And so that's another case of U substitution, where we did it in the very beginning of class, but throughout the class we have it sprinkled into some of our problems.